just one short presentation, and then we can break. Now for a real change of pace, we've got a student who is not from Purdue who is going to be speaking. Sophia Porter is a sophomore at Johns Hopkins University, double majoring in physics and applied mathematics. She's a Woodrow Wilson Research Fellow with an upcoming publication in the APJ, that's Physical Journal. She enjoys projects which employ both artistic and scientific knowledge, particularly when they have potential to make challenging topics more accessible to the public. She also has an extensive background in astrophotography, image processing with the Hubble Space Telescope, and she spends her free time singing with her a cappella group and gardening. Sophia Porter.
Thank you, Harley. So I am a student at Johns Hopkins, like Harley had said, and as an undergraduate, it's not super feasible to have a car in the city. It's kind of expensive, it's hard to find parking, and so my primary mode of transportation is Uber. And this usually works out pretty well for me. And every once in a while, my parents come and visit, as they have this week, and I Uber back and forth to their hotel. And one night, a couple of months ago, it was getting chilly out and it was kind of late, and I called my Uber from the lobby of the hotel, and I was sitting there watching the minutes tick down on the app, 7 minutes away, 6 minutes away, 5 minutes away. And finally, the app said, "Oh, your Uber is arriving." Great. I walked outside, there it was. I hopped in the back and I said, "Hey, Jeff, how you doing?" And the driver didn't say anything. And I said, "Hey, Jeff, how's it going?" And Jeff just didn't respond. And finally, I turned around my phone and I showed him and I said, "Hey, Jeff, I'm headed to Johns Hopkins. How are ya?" And he looks at me like I'm absolutely insane and he says, "I'm here to pick up my wife." And I learned a valuable lesson that day. I learned that things are not always as they seem. Things are not always as they seem. And that has been true for me for a long time. Things have been different than they seem. Fundamentally, that's true because I grew up being an artist. I grew up loving art. I painted, I drew, and I also aspired to be a scientist. And I've loved science since I was young. In first grade, I wanted to be a paleontologist. I love science. It's fundamentally a part of who I am. But I was told ever since I was young that my interests didn't mesh, that they were fundamentally different from one another, that they couldn't communicate, and that ultimately I was a walking paradox. It didn't make any sense. And I actually had the opportunity to reconcile the differences between the two 2 years ago at the Goddard Memorial Dinner, where I delivered the keynote speech and talked about the similarities that I have found between art and science. And I thought, great, you know, I gave my speech, it was wonderful. I thought, all right, that was that, now on to something else. And as I found out, nothing is really ever finished. Once I got to school, once I started studying physics and mathematics in undergraduate, I learned that there are so many more similarities between art and science than I ever could have imagined. There are so many more similarities, and I really want to share them with you because I think the implications are incredibly valuable. So when I started studying physics, one of the first things I realized is how fundamental math is to the field. If you can't speak math, it's really difficult to do physics. And so one of the first things that I asked in trying to reconcile the similarities between science and art, and particularly physics and art, is what is math? What is this thing that so fundamentally informs physics and is the language of physics? And the more I thought about it, the more counterintuitive that question became. What is math? I kept asking myself, what is it? I studied math for, since kindergarten. We've all studied math since kindergarten. And I couldn't answer the question, what is it? And I actually took the question to the head of undergraduate mathematics at Johns Hopkins. I said, "Dr. Brown, what is mathematics? How do you define the boundaries of math?" And he said, I see you caught the bug. And I received a Woodrow Wilson Fellowship grant to pursue that and questions very similar to it. And in January of this year, I traveled to the Joint Mathematics meeting where 6,000 mathematicians get together and talk about issues that are fundamental to the field. And I interviewed over a dozen of them. And I asked each of them, what is mathematics? And their answers really stunned me. In fact, I wrote them down because I have to read them word for word. I have to quote them. Mathematics PhDs said things like, I don't feel qualified to answer. I haven't given that much thought to it. And as many times as I've been asked that question, you'd think now I should be able to answer it. And even things like, I'm not a mathematician, so I haven't thought a whole lot about that. Okay, it was actually an electrical engineering PhD who said that. But the point is that people who spend their lives doing mathematics, people who spend their lives learning and studying and loving the field, have trouble defining what it is. And I thought, well, boy, if people who love mathematics can't define it, how do we expect young students, how do we expect elementary school students to appreciate it, to fall in love with it, if they don't know what it is they're falling in love with, and if their teachers don't know what it is they're trying to communicate? Well, I had this discussion with over a dozen mathematicians, and eventually we settled on kind of a collective definition, and that is that mathematics is the study of pattern and structure. Pattern and structure. The artist in me said, wow, that's like the first thing you learn in art class. I was really blown away, and I thought, well, boy, pattern and structure are kind of fundamental to art. And in fact, they're fundamental to all art, even the most abstract art. And by abstract, here is one of the more abstract pieces I know of. This is Jackson Pollock, who was a drip painter. And I say drip, he wasn't really a splatter painter. It was a very intentional type of artwork that he did. He didn't throw paint at a canvas. He very carefully laid the paint down where he thought it ought to stay. And I would argue that this has a pattern, because if I were to cut off a corner of the painting and show it to you, you could identify the original. To me, that says pattern. Not only does it have a pattern, but it has an underlying meaning, because he named it autumn rhythm. And that doesn't necessarily mean anything to me, autumn rhythm, but to Pollock, this piece very clearly represented an autumn rhythm. So even if the meaning isn't instantly clear, clearly it has meaning, and it has pattern, and it has structure. Just like mathematics. Not only are the pattern and structure the same, but I think the underlying languages are written in a very similar way. A fellow student of mine actually wrote a mathematical poem. Oh, excuse me. Here we are. He wrote a mathematical poem where he derived the equation for a 3D harmonic oscillator. And he wrote, there was once a two-body interaction. Acting with T hat showed no reaction. So we changed the frame, leaving H hat the same, reducing our work by a fraction. And this goes on for several pages, where he continues in both English and mathematics to define the 3D harmonic oscillator equation. And I think this is wonderful. And one of the reasons it's wonderful is because I applied an artistic technique, and it's a technique called squinting. The idea is that when you're looking at something, when you're trying to break it down into the shapes and colors that make it up, you squint at it, so that you lose the fine details and you're left with the general shape. And I think that if you squint at this, the mathematics and the poem itself begin to look very similar. And in fact, if I were to write a poem using the language of mathematics, this is exactly how I would do it. And I would call it a proof. Clearly, art and mathematics have a similar structure. And they actually communicate really well, even in some of their results. If you type the word fractal into Google, I really couldn't tell you whether these are pieces of artwork or demonstrations of mathematics. They're clearly informed by artwork. The colors are chosen artistically, but the patterns are chosen mathematically. But what really fascinates me about this search, and the reason that I had to screenshot it, is because of the Google search suggestions. If I wanted to look further into this, Google suggests that I should look at ancient art, or fashion, or nature, or most shockingly to me, love. Love, all because I typed in fractal. Wow, that says to me that people who search fractals, mathematicians and non-mathematicians alike, also think of love when they think of fractals. There's something emotional happening beneath the surface of the mathematics. It's touching people in a way that formulas may not. Somehow, this visual aspect of mathematics, this visual aspect of fractals, has an emotional impact on people, and I think there's something to harness there. So, it seems to me that math and art have these interesting structural similarities, but I also think they have theoretical similarities as well. And one of the most interesting things that I've learned about mathematics since I got to school is that it doesn't exist in the physical world. Mathematics doesn't exist in the physical world. This was incredibly counterintuitive to me at first, but I want to try and prove it. So here is my best attempt at drawing a point. It's a point, I just put it together in PowerPoint. But the truth is, if we were to blow up this point, it's really not a point at all, it's a circle. And no matter how small I were to draw the point, I could always blow it up into a circle. And the truth is that the circle wasn't a great circle after all. No matter how I drew it, no matter how precisely, how perfectly round I drew it, it would never truly be a circle. So I can't draw a circle, and I can't draw a point. And the truth is, there are many other things which I can't hand you. Think about the number 3. I could hand you 3 of something. I could hand you 3 apples. But I couldn't really hand you the number 3. No mathematical object has a physical presence. And when we bring it into the real world, it's only an approximation. Think about the Earth that we're standing on. Is it a sphere? Well, it's mostly a sphere, but that's really just an approximation. There are mountains and valleys and hills and troughs. It's not really a sphere. But it's a pretty good guess. It's a pretty good approximation. And I think you could kind of make the same case for art. This is a painting by Edvard Munch. It's called The Scream. And I think the background for this painting is really interesting, what Munch writes that he experienced when he made the painting. He says, "One evening, I was walking along a path. The city was on one side and the fjord below. I felt tired and ill. I stopped and looked out over the fjord. The sun was setting and the clouds turning blood red. I sensed a scream passing through nature. It seemed to me that I heard the scream. I painted this picture, painted the clouds as actual blood. The color shrieked. This became the scream." To me, what Munch is saying is that he experienced the clouds as blood. To him, in that moment, the clouds really were blood. And the best that he could do to help us feel that was to paint it, to approximate it on paper, to bring the pure and abstract feeling that he experienced into the real world via an artistic interpretation. Munch intended for us to understand the feeling. He wanted to communicate it to us, and the best he could do was approximate. And the truth is that science is also very much the same. This is a formula that some might consider beautiful. It tells us how fast we need to be going in order to escape the gravity of the Earth, how fast we need to send something up in order to get it out of the Earth's gravity. It's simple, it's intuitive, it's clear, it involves a few measurements, and that's it. But the truth is, if we were really to try and send something into space, well, then we've got to start thinking about error. On every measurement we make, there's going to be error. Just like the Earth isn't a perfect circle, so when we try and write down the radius, well, are we talking about the radius to the peak of a mountain or to the bottom of the ocean? We have to approximate. We have to approximate, and as those of you who are engineers may know, this isn't even enough to get us out. Our error is going to be much more complex. There are so many more layers, and even if we tighten the error bars, we will never have perfectly the escape velocity. The number exists, it's out there. There is a velocity that will get you off of the Earth. But when we plug in the data that we have to include the error. We follow the scientific method. The scientific method is something that students learn when they're asked to do science fair. It's pretty straightforward. It's a couple of steps. You make an observation, you ask a question, you generate a hypothesis, make an experiment, and interpret and apply the data that you get from the experiment. But I also believe that there's an artistic method, and I think that it very closely parallels the scientific method. I want to tell you about the artistic method. Instead of making an observation, an artist makes a personal reflection. Instead of asking a question, an artist seeks to express something that doesn't exist yet, to fill the void. When they make a hypothesis, an artist plans a creative work, plans out what they want to bring to the world. The experiment is to create the work itself. And in place of applying the data and interpreting the data, they share the work with the public and leave the interpretation open. This is the artistic method. The goals of art and science run parallel. The goal of science is to study the universe. The goal of art is to interpret the universe. Science seeks to study the universe. Art seeks to interpret the universe. That says to me that creativity and imagination are the abstract form of artwork, which is physical. Just like mathematics is the abstract form of physics and of science. Creativity is what we experience and what we try and communicate via art, just like mathematics is the pure and crystalline truth that we approximate using science, that we bring to the physical world using science. There's a wonderful parallel. And the truth is that I no longer feel like a walking paradox, because there are things like this. This is a photo that I created in an internship with Zolt LeVay, the Hubble imaging lead at the Space Telescope Science Institute. This is data taken from the Hubble Space Telescope, but a lot had to happen, like Matt Mountain had mentioned this morning, a lot had to happen between the data that came out of the telescope and this final product. Hubble takes pictures in black and white, and first we have to stretch the data, and then in order to colorize it, I have to select different spectra and assign one to be red and one to be blue and one to be green. And I pull them into Photoshop and I tell Photoshop, stack these so that the red, blue, and green talk to each other and they overlap with each other and create all of the colors in between. And not only that, but the artifacts that Hubble leaves and the dead pixels and the cosmic rays are blocking some of the data that really belongs in that picture. And as an artist, it's my job to scratch those out and put in what I think belongs underneath them, what I assume the nebula looks like underneath them. Is this a piece of art or a work of science? It's hard to say, and I think it's both of them. I think it's both of them because it would be impossible to create things like this without using both art and science. And if I were to ask someone, what does this nebula look like in real life? It would look incredibly different to the Hubble telescope and to the human eye were we there, but this is the best approximation that we can make. This is the best artistic and scientific approximation. And I think it's an indicator of the very close relationship between art and science. One of the biggest questions in physics today is, what is dark matter? What is dark matter? What are the properties of it? How does it function in our universe? Thousands of physicists have spent thousands of hours working on this question. And I think that if we applied the artistic method, if we reflected on what we'd seen and thought outside of the box, and used techniques that hadn't been tried yet, and maybe things that are completely new to science, we might get one step closer to finding the answer. Not only that, but I think there are thousands of students out there today who know that they are artists and believe in art and think they're not cut out for science. And I've heard so many times, science is too hard. Science is too hard. Mathematics is too hard. I'm afraid to study it. I don't like that class. I don't enjoy the study. But I have never once heard someone say, art is too hard. I think those people who say that don't understand that they could apply their artistic process to science and have great returns. And I'm actually drawing on a personal experience when I say that. When I was in 3rd grade, my teacher handed me 2 wires and a battery and a light bulb and said, using these tools, you can make the light bulb light up. And to me, the physics for that didn't exist. I had no idea how it worked. It was a mystery. There was no theory, there was no textbook. It was just me and my experiment. And it took me a while, it took me a half an hour, but I put the pieces together and finally I did make the light bulb light up. It was really a light bulb moment for me. I mean, I felt like Thomas Edison. I had just invented my own physics. It was a triumphant moment, and I remember it very clearly even today. And I think if every student, K through 12, had 12 of those experiences, if they made physics work for them, if they invented it, if they felt like they owned their tools 12 times, can you imagine how excited they would be to attack problems that nobody has ever handled before? Can you imagine how excited they would be to apply their creativity and ingenuity and their artistic method to the problems facing science today? Science is a growing field. It never shrinks. We only add information, we add data. The field is always expanding. And the more that it expands, the less any individual can understand the entire field as a whole. We're past the days when 2 Wright brothers can build a plane. We need a team of engineers. We need communicators. We need people who can take ideas from their mind and express them very clearly, just like Edvard Munch expressed the idea of bloody clouds. We need people who are comfortable expressing these ideas and sharing them with others, and I think nobody is better suited to that than artists. There's so much untapped talent that we haven't harnessed yet, and that we could harness. I think we need to take science as a brush, and we need to take mathematics as paint, and we need to put them in the hands of creative students and let them create. Let them make their own light bulbs light up. We need to tell students how creative the field really is. Each of you found a spark of passion. Each of you found something that you love about the field. Share that with one student, with 3 students. Let them know what you see in the field. Let them know how creative you can be and what powers you exercise and what you create. I want to leave you with one final thought. We play music. We create art. What if we could perform science? Could we show students that science is so much more than equations on a paper, that its mysteries unfolding, and that its disciplines meeting, and that it is data coming to life? Are we willing to reimagine how we portray the field to the young and to the curious? Are we willing to play and to be creative and to perform? I promise, as we do, that many young minds will follow in our footsteps and paint their own creative masterpieces. Thank you.
And there's a reception down around the hall. Follow folks who know how to